Okay, guys, we'll get started in a minute or two. Just wait for a few more people to sign in. Okay, we'll go ahead and get started now. It's about 30 seconds till 10, so I'm starting a little bit early. All right. I did post this announcement yesterday, and it gives us sort of a laundry list of the end game here. All right, we have this will be the last of the worksheets, this one today. Of course, I'll have to get busy and post all your grades for the worksheets. So that'll be first on my agenda next week to get all your grades posted for the 12 worksheets. And then remember, on the worksheets, I take your 10 best. So if you didn't turn one in, or if you got a low grade, whatever it is, I'll take the 10 best and eliminate the 2 lowest. Okay. All right, so I will post the video of today's session as soon as possible. And this current worksheet, I will post the solutions probably sometime on Friday. They're due Friday midnight. So your worksheet 12 will be due Friday midnight. And today we'll go over the solutions in pretty good detail, but remember, you can always look at the video and then you're also on the hook for the StatCrunch session. Okay. So you've been sending in your worksheets along with your .scs file with all of your StatCrunch actions. And so, you know, what you've gotten out of this course this semester is a good overview of all of the statistical procedures that encompass elementary statistics. We don't go into a lot of depth mathematically because that wasn't our objective. Our objective was to introduce you to statistics at a introductory level, provide you with StatCrunch, which if in the future you served as a statistician for someone, you would be able to use your StatCrunch to great you know, to great advantage. All right, hopefully. So, so hopefully you got something out of this semester, and it's always tricky with a virtual class. It's really not the same, is it? But hopefully with Canvas, with MyLab Statistics, with StatCrunch, at least, you know, you had a vision of how all the pieces fit together. Okay. Now, next week is Thanksgiving. So all the classes are closed next week. And so we won't have any Zoom sessions. Some of you will probably hunker down and get caught up on your homework in MyLab Statistics. It's been a while since we did the progress check. And so a few weeks ago, the average completion rate was right about 50%. So I'll check that again, and maybe I'll send out a reminder for MyLab Statistics. It's very important. It's 25% of your grade. It's equal in weight to your exams and your homework. So those 4 elements constitute your grade. Okay. And the when the clock strikes midnight on Monday, December the 14th, MyLab Statistics will close. So you still have ample time to catch up if you're behind. All right, if you're making good progress, you should have, we're going over the exercises in chapter 12 today, which is the last chapter that we'll cover from the textbook. Okay. And so let's see, what have I not covered on this? The final will come out during the last week of the semester. Okay. And remember, that week is the week of December the 7th. Monday, December the 14th is the last day that the college has run this 16-week semester. So you'll all be, you'll have all your work in by midnight, December the 14th, and then I'll get busy and spend the week after that parsing all your work and coming out with the grades. And it's very easy. It's just the average of your 4 pieces, your 2 exams, your worksheets, and you should know your final grade for your worksheets probably, let's see, in 2 weeks. Okay, today is Tuesday. Next week is our Thanksgiving week, and then the following week, you'll see all your grades posted, and you'll be able to calculate your worksheet grade out of 100. You already have your midterm, and the only 2 pieces left are your final exam and your MyLab Statistics. Okay, and please contact me if you have questions. I did get a lot of email traffic the first 8 weeks of the course. It's kind of slowed down a little bit in this last part of the course, but I'm always there. Some of you have sent me emails, and I've tried to respond to you as quickly as possible. All right. Okay, so let's now move over to the any questions about the final part of the semester here. Any questions? Okay. All right, let's get started then. Let me just check the waiting room here. No, we're all good. Okay. All right. So let me open the file here and go over the solutions with you. to this last worksheet, and I'll explain the subject matter, and I'll explain the techniques in StatCrunch, okay? All right, what we're studying in chapter 12 is the analysis of variance. Now, you all know what the variance of a sample is, and it's interesting because this procedure is a test of the equality of more than two means. Now, back in chapter 9, we studied the hypothesis test and the confidence interval for testing and estimating two means, okay? And there were a number of assumptions that allowed us to create those tests in a mathematical manner. And with this procedure, with more than two means, testing the equality of more than two means, we still have some mathematical assumptions. We won't go into those in any depth. The primary assumption would be that the variances are equal for all of the samples. There will be K samples. K will typically be greater than or equal to 3. Okay, so we'll be sampling from populations with the same variance, sigma squared. Okay. And I'll explain to you how we set up the test statistic for this type of test, the test of multiple means, okay? So let's go ahead and start in with the first problem here, okay? And I'll read it and then we'll do our calculations. Jeff Parent is a statistics professor who participates in triathlons. Listed below are times. Oh, by the way, these exercises are from chapter 12, section 1 on one-way, so-called one-way analysis of variance. And so these are some problems that were taken right out of your textbook here, okay? All right, let me, oh wait, yeah, let me put it in full view here. Okay, so you can go back into your text and refer to section 12.1 as you go through these problems, as you write them up yourselves, all right? So listed in the table are the times in minutes and seconds he recorded while riding a bicycle for 5 stages through each mile of a 3-mile loop. Now, here's a familiar parameter, the 0.05 significance level, and we'll test the claim that it takes the same time to ride each of the miles, okay? And so we have these 5 stages. We've recorded his times for each of the 3-mile legs or loops. And at each of the 5 stages, the times are recorded, okay? All right. So again, we'll use our procedure of listing the null and the alternative. So what we're going to do is test at the 0.05 significance level a claim that it takes the same time, and we're talking about the average time to ride each of the miles, okay? So here we have each of the loops. They're a mile in length, and these are the times at the 5 stages that he recorded. Now, what I have here is the StatCrunch results, and I'll show you how to generate these results. Unfortunately, when I go in from my word processor document, which looks perfect, and upload it into Canvas here, it kind of throws off the word processing a little bit, and we've seen this before. So just remember that any numbers that fall in this space here belong upstairs with the rest of the numbers, and you'll see that in several of these little boxes here. And I don't know how to repair that. We can't do any editing once it gets uploaded into Canvas. So, all right, so let's skip down a little bit. I'll come back to how I derived these results in StatCrunch, okay? And StatCrunch will generate what's called an F statistic, F being the new distribution that in fact is used for this test. Okay, now from chapter 11, we saw that there was a chi-square distribution, which is the theoretical distribution for the goodness fit test, the test of independence, and the homogeneity test. And then back in chapters 8 and 9, we saw that the two distributions, the normal distribution and the t distribution, were the mathematical distributions that allowed us to test and create estimates for a variety of tests, okay, and proportions, all right? And remember, the t distribution was really a family of distributions. So was the chi-square. This new distribution, F, is also parameterized by degrees of freedom, and I'll get into that as we explain this solution here. All right, so let's imagine that we performed a test with a test statistic in analysis of variance. The test statistic is called the F distribution. So what StatCrunch will give us are the means, okay, for each of the mile loops. And what I've done here is I've converted these times that are displayed as they normally would be in any type of bicycle race or foot race in minutes and seconds. And then I've just converted all of these times to seconds. So these means are given in seconds. So if you were to convert each of these, and you'll see that in StatCrunch when I show you the StatCrunch calculation, okay? So for example, 3 minutes and 15 seconds is 195 seconds. 3 minutes and 24 seconds is 204 seconds, and so on. So when we go into StatCrunch, you'll see these times expressed in seconds. And so when StatCrunch calculates the summary statistics for these measurements, these are in seconds, okay? All right. So we come down to the next table here, and in this 1, 2, 3, 4, 5, in this fifth column, we see the F statistic, all right? And along with the p-value, we will reject or we will not reject this null hypothesis that they're equal against the alternative that they're not equal. Another way to say that is that at least one of the means is different, okay? And then what you see here in the p-value is a very low p-value. And just as in our chi-square test and our z and t test, if the p-value is low, h naught is a no-go. All right, we'll reject the null hypothesis in favor of the alternative. Well, what is the alternative here? If we don't accept or if we reject the null hypothesis, the alternative is that not all the means are the same, or at least one of the means is different. So one of the things that we're going to do here is try and interpret the result. And if we don't reject the null, or even if we do, does the data indicate to us that one of the means is different? Certainly, if the null hypothesis rejected, we can state that at least one of the means is different. If it's not rejected, we still may be able to see some differences there, but they won't be significant at the 5% level. That'll be the caveat. All right. Now, there's something here in the second column in the second table called degrees of freedom, or DF. We saw the chi-square and the t distribution. We worked with the data there to understand what the correct degrees of freedoms is. And that was important because we have the other approach, and that is finding a critical value under the F distribution such that in the right tail, beyond that critical value, you have exactly 5% probability. Okay, so we're going to have the classical notion of a critical value as well. All right. Okay. Now, here I've listed the step 2, which would be to compare our p-value to 0.05, noticing that it's much smaller than 0.05, so that puts us way out in the right tail, and so we would reject. Okay, and our conclusion is that at least one of the means is different. So that's an overview of how the F-test works. And you're probably wondering, well, how do I calculate my F-stat? And how do I calculate my critical value for this test? All right, so we'll talk a little bit about that now. Okay, so here's a paragraph summarizing our decision making here. In StatCrunch, we calculated the F statistic, we calculated its probability value, and we made a decision of whether to reject or not. Okay, so let's read it up here. There is sufficient evidence to warrant rejection of the claim. That came right out of the previous step 3, comparing the p-value for that F-stat. All right. So there is sufficient evidence in these sample data to warrant rejection of the claim that the 3 samples come from populations with means that are all equal. Okay. And using the samples of measurements listed in the table, we conclude that those values come from having means that are not all the same. Okay. So on the basis of the ANOVA test, we cannot conclude that any particular mean is different from the others. Now, in the statement of the original problem, it was posed, does one sample appear to have a hill or something that might have slowed down the triathlete here? Okay, so even though we rejected the null hypothesis, okay, so we conclude that at least one of the means is different. It looks like in mile 3, notice that in mile 3, the average time was a little higher. It was 210.8. All right, so that rejection of the null And so it raises our suspicions that one of the means is different, and it could be mile 3. All right. Certainly at the significance level, it looks like it might be mile 3. Now, we could do t-tests of the 3 pairs of the 3 mile loops, and but that is not the technique that we're going to do. Instead, we're going to consider all the means at the same time and use the data as evidence of whether to reject or not. Beyond that, we have to be very careful about stating which of those means it might be that's not equal to the others. Okay, but certainly mile 3, because it has a higher mean, all right, it may be that it would be different in terms of the average time it takes. It might be a little more. Okay. Now, the critical value is, I want to do a little bit of discussion about how we actually put the test, how we put the F distribution together. And it turns out to be a ratio. Remember how the chi-square was defined? The sum of the observed minus the expected squared. So there you're comparing the square difference of the observed and the expected frequencies. You're normalizing by dividing by E, and then you're adding. And we saw again that if that value was too high, we would reject the null hypothesis that there was a good fit. Okay, so we're doing the same thing here. We're not taking differences, we're taking ratios. So we'll have something that we'll call the variance between the samples. And remember, I indicated that the variance for all of these populations from which we sample is the same. The variances are the same, okay? And then we'll compare in the denominator the variance within the samples. Okay, so that also plays a role, all right? So even though if you have 3 samples where it looks like the means are close together, what about the variation in the each individual sample itself? That's gonna come into play here, okay? And so what we'll do now is calculate the variance between the samples in the numerator, and then compare that with the variance within the samples. And if that's too large, in other words, if the numerator is much larger than the denominator, we will reject the null hypothesis. Okay, all right. So the numerator of the F test statistic measures variation between the sample means. Okay, so we look at the X bars, and we have N of those, where N is the number of samples. And we have to see how those vary, what their standard error is, and then we'll compare it, the estimate of the variance in the denominator depends only on the sample variances and is not affected by differences among the sample means. Okay, so that sample of the first mile loop stands alone in terms of its variance. It might have a different variance than the average of the second, and so on. So we'll take the ratio of the 2 variances and see if it's too high or not. If it's too high, we will reject. Okay. All right. So in general, sample means that are close in value to each other result in a small F test. In general, we can cook up examples where we can have the sample means looking close, but then the variation within the samples throws us off. Okay, we might have a lot of spread in that particular sample of size N. we'll consider in this one-way analysis of variance that we have equal sample sizes across the K samples. All right. All right. K is 3 in this case. We have the 3 loops, mile 1, mile 2, mile 3 loop. Okay. All right. So in general, though, if we have a large spread in the sample means, that'll give us a clue that we have a low p-value. We're way out in the right tail of this distribution, and we will reject the null hypothesis. Okay. All right. So let's get a handle on what that numerator is. Well, we talked about the variance among the samples, and remember that sigma squared is the assumed variance of all of these K populations, and sigma squared over n is the population variance when we have n samples, okay, when our sample size is n. So sigma squared over n. So what we're going to do is use n sigma squared and s squared, okay, the sample variance of the x bars. Okay, so here we have our x bars up here in seconds: 201, 199.6, 210.8. And so we can take the variance among those 3 values, x bar. And if we multiply by n, then we get an estimate of sigma squared. Okay, so that'll be our numerator, right? And in this problem, we saw that the 3 sample means for the 3 loops were 201, 199.61, and 210.8. You see that? Okay, so again, if we were to take averages in seconds for mile 1 and calculate the summary stats, we would get a mean of 201 seconds with a standard deviation of about 3.5. Okay, so now we're going to take the variance in that sample of x bars. It's a small sample, it's only 3, but we can still take its variance. And it turns out that when you calculate the variance, again, you can do that in StatCrunch. All right. So, all right, sample variance is 203.8, and we get here that n s squared x bar, and we get this result here. Okay, this turns out to be the variance. Let's see, 3.8. Okay. Let's see. This I'll fix this. This should be the sample mean. Okay, if you take the average of these 3 values here, somebody do that out there and make sure that it's 203.8. Okay, and the turns out the variance of the 3 values, that is the variance of the 3 x bars, the sample variance is s squared sub x bar. Okay, and if we multiply that by n, because remember the variance of the sample mean is sigma squared over n. So if we replace sigma squared by s squared of x bar, multiply by n, then we'll get an estimate of sigma squared. And that turns out to be, in this problem, 185.99. Okay. Now let's go back and take our average of the 3 sample variances of each of the 3 mile legs. Okay. All right. And how do we do that? Well, we just square the standard deviations. So take these numbers here. These are our standard deviations. Square those, we get the sample variance. And then take the average of those, and that'll give us what's called the variance within the samples. Okay, here's our denominator here. That's the variance within the samples. That's also known as the pool variance, isn't it? Okay, so if we take that average, add up the squares of those 3 standard deviations, we get the value 6.85. So our F statistic is the ratio of n s squared x bar, which is 185.99, and the pool variance here, the mean of the sample variances, is 6.85. So when we take that ratio, we get 27.15, and that's our F statistic. Now, up here, you see that value expressed as 27.25. So there was a little bit of rounding error, but essentially those are the same value. Okay. So here's our F statistic, and now we'll come to the critical value here. And I think what I'll do is I'll go into StatCrunch now, and we'll do the calculations in StatCrunch. So let's do that. Okay, now here's our StatCrunch data set here. And remember that for each of these 3 mile loops, I've listed the data in seconds. Okay, so these are the same numbers that you saw in the original table given to you in minutes and seconds, and just multiply the minutes by 60 and add the seconds, and you'll convert all your data into seconds. Now, some of you might say, well, why can't I take the seconds and convert those into decimal of minutes? Yes, you could do that. 3 minutes and 15 seconds is 3.25 minutes, isn't it? So you could express these numbers in fractions, in decimals, okay? And so here are the 3 values here. And let's do 2 things now. Let's do the StatCrunch calculation of the F stat. And again, we'll go to the stat super function here, and notice that in this list, you've probably ignored it all semester because we didn't need it, but here you have ANOVA. So we're going to use the ANOVA function. We're going to use it in the one-way manner. Now, I'm not going to cover section 2 in chapter 12. That talks about two-way ANOVA. We don't have time to cover that. So we're restricting ourselves to one-way here, okay? So when we click on the one-way option, we get, again, the action window, the dialog window here. And what we'll have to do is specify the columns where the 3 data sets reside, okay? Hold on just a second. Okay. And here they are. They're listed in the columns. And we're going to choose mile 1, mile 2, and mile 3. Okay. So again, by using command click, you can select any of these columns that you see coming up in the column window. Our test is going to be over these 3 samples here, okay? And I also wanted to show you the dot plot. I didn't put it in the solution set for this problem here, but let's look at the dot plot as well. Okay. Okay, so here's our result, and I copied and pasted this result into my document, just as you see it here. And again, to remind you how to do that, you could do a Command A, and then do a Command C, and then go back into your document and paste it right in. All right. I also wanted to show you the dot plot here. And here's what we see. We see that mile 3 here, okay, here's mile 3. And you can see that it's not too spread out, is it? Okay. Neither are the other 2 miles. There's one little outlier here in mile 1. Okay. But in mile 3, we definitely see a shift out here. And it did turn out that the mean was 210.8. Okay, but the variance of this sample looks to be not very large. This variance here is a little larger, okay? And so we do see an evidence of some difference in the means there. It's an eyeball, okay? So there we have our F-test, and then the other part of this is to calculate the critical value under the F distribution. So what we'll do again there is we'll determine the degrees of freedom for the particular F distribution we're using here. And then with those degrees of freedom, we'll be able to select the correct F distribution from our calculator, our stat calculator here. And before we do that, I want to go back to the document and show you how we select the degrees of freedom. Okay, so here you see a list of distributions from your calculator function, and there you see the F distribution here. Okay, so let's go back to the document. I want to explain to you what those degrees of freedom are. All right, so we go back to our document here, right? And again, we know that when the ratio is large, the ratio of the variance between the samples over the variance within the samples, if that's large, we're going to reject, okay? All right, so what does large mean? Well, that depends on the critical value. It also depends on the p-value, but we're now focusing on the critical value, okay? So how are the degrees of freedom defined? We'll have a pair of degrees of freedom for this problem, and we'll call them the degrees of freedom of the numerator and the degrees of freedom of the denominator. And how do we calculate these degrees of freedom? Well, mathematically, the numerator degrees of freedom is just the number of samples, k, minus 1. Okay, it looks like a t. Remember t when we had n minus 1 as our degrees of freedom there. So the numerator degrees of freedom is given as k minus 1, where k is the number of samples. In our problem here, k is 3. We have the 3 mile loops, okay? And for the degrees of freedom for the denominator, the formula is K times n minus 1, where n is the size of each of the samples. Now remember, in this one-way analysis of variance, we're assuming that all the sample sizes are equal, okay? And they each have sample size n. In our problem, we had 5 values taken at the 5 stages for each of the mile legs. And so our degrees of freedom for the denominator is K times n minus 1. So for this problem, with a sample size of 5 for each of the mile legs, we just get 3 times 5 minus 1, which is 12. Okay? So these formulas here are what we're going to use each time to calculate our pair of degrees of freedom. One of the pair for the numerator and the other degrees of freedom for the denominator. So that results in degrees of freedom for the numerator is 2, degrees of freedom for the denominator is 12. Okay, now let's go back to StatCrunch and calculate our critical value using the F calculator. So again, we'll go back to Stat Calculators. We'll choose the F distribution here. And this is your first look at what the F distribution looks like. It's a right skew distribution. It looks like the chi-square a little bit. It's positive. It's positive because we're taking ratios of variances, and variances are always positive. So this distribution will also be positive here, so it extends from 0 out to plus infinity. The area under this distribution is always 1. It's a probability distribution function, a PDF. And what we're going to do is give it a pair of degrees of freedom. One for the numerator, which is 2, and the other for the denominator, which is 12. Okay, those are the two numbers of degrees of freedom that we calculated before. All right. We'll specify 0.05 area in the right tail, and we'll reverse our inequality there so that the shaded area represents the area to the right of this critical value, about 3.9. Okay, so here's our critical value given to us using the FStat calculator. All we had to do was set this up, give it the right degrees of freedom for numerator and denominator, set our tail probability to be 0.05, and then calculate our critical value as the probability that the distribution exceeds the critical value is equal to 0.05. Okay? So that means that here we've listed our critical value for 2 and 12 degrees of freedom, and at the 5% significance level, it turns out to be 3.89. It's much smaller than our FStat. Okay, remember our FStat was over 27. So that would allow us to conclude that since this FStat is to the right of our critical value, we would reject. Okay. Okay, so that's a lot of theory and practice and StatCrunch all in this first problem. Any questions? Any questions about what we're doing here? Okay. All right. Okay, let's go to the next problem now. Oh, and I've recreated that critical value graph in the solutions here. Okay, I've copied and pasted that graph right into the document. Just to back up our statements about the critical value and the decision based on the critical value. Our next problem, number 12 in your textbook, states the following. Listed below are amounts of arsenic in samples of brown rice from 3 different states. The amounts are given in micrograms, and these are micrograms of arsenic. And you know that arsenic is a highly toxic substance. All samples have the same serving size, okay? And how many serving sizes do we have? How many samples in each serving size? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so here are the 12 servings from the 3 different states, Arkansas, California, and Texas. All right, so that's our data. And we'll go ahead and list our data as we did in the first problem in columns in StatCrunch in order to perform our FSTAT test. And K is 3 here, as it was in the first problem. We have the three states. So across these 3 states, we have 12 measurements. And our null hypothesis is that the mean number of micrograms of arsenic, okay, that these means are all the same, versus the alternative that at least one of the means is different. Okay. Again, we'll set the significance level equal to 0.05. And now let's go back to StatCrunch and perform our test. Okay. Okay, so here I've copied the data from the problem into StatCrunch here. And these are micrograms of arsenic in the portions here, okay? And inspecting the data, you know, we might look at the dot plot. I'll show you the dot plot, and we'll try and observe the data in a dot plot to see if there are any differences. But that's not necessary. We can go ahead and perform our FSTAT test. So let's do that. We'll interpret the results when we get done with this test, okay? So let's go to our ANOVA again, choose one way, and then choose these 3 states here, Arkansas, California, and Texas. So these 3 states here now, we'll look at the hypothesis test. The mean amount of arsenic is the same across the 3 states, okay? And I'll show you the dot plot as well. Okay, so here's our result from StatCrunch. And the sample sizes are 12 for each of the 3 states. Here we've calculated the sample means and the standard deviations, okay? All right. So are these means significantly different or not? Well, let's look at the FSTAT. The FSTAT is pretty high. The p-value is very low. So we would reject the null hypothesis and conclude that at least one of the means is different, okay? And then if we look at the dot plot here, we can see that Texas is shifted a little bit to the right. The spread of the data for Texas is not very high, and we saw that in our summary stats in the FSTAT results. Okay, here's our variance. It's about 6.9. Sorry, I'm looking in the wrong column. Our mean is about 7 here, right? Our variance would be the square of 0.691945 And, that's about the square of 0.7, which would be about 0.49. So the variance is not very high, okay? And the only large variance we get is California. But we do see a significant difference in the mean here. And it's quite likely that Texas, the average is different. Okay, we would have to do a closer analysis to make that mathematical conclusion there. Okay, but in the dot plot, we can see not too much dispersion in the Texas data, not very much dispersion in California or Arkansas, but we can see that the Texas mean is probably significantly higher than the other two means. But we can't actually state that. We can make a conclusion that that's probably the case, but we'd have to do some more analysis. And section 12.1 does give you some clues on how to go from here and how to pin down the fact that Texas might have a different mean. All we know is that at least one of the means is different. Okay. All right, so that's our analysis. And then the final step would be to calculate the critical value. Let's go back to our document. Okay. Okay, so again, to recap our interpretation here, using the samples of measurements, we conclude that those values come from 3 different states, that they have on the basis of the SANOVA test, we cannot conclude that any particular mean is different from the others, but we can informally note that even though Texas has the highest mean, we can't definitively say that brown rice from Texas poses a health problem, okay? Okay, so again, for our critical value, we need to calculate what the degrees of freedom are for the numerator and the denominator. K is 3 here over the 3 states, and K minus 1 is 2, and K times N minus 1 is 3 times 12 minus 1, that gives us 33, okay? So if we pull up our F calculator in StatCrunch, let me show you that here in the document. Okay, here it is here, right? So if we go to the calculator, put 5% area in the tail of this distribution, and this represents an F distribution whose degrees of freedom for the denominator are 2, degrees of freedom for the numerator are 33. And we identify the critical value to be about 3.3, okay? And that's summarized up here, okay? Critical value is less than the F-stat. P-value was very low, close to 0. So that would lead us to reject the null hypothesis and state that at least one of the population means across the 3 states is different. Okay? Any questions about number 2? Okay. All right. And your StatCrunch. Any questions about StatCrunch? How we did the F-test in StatCrunch? Again, take your stat super function, pick one-way ANOVA, and then choose the correct columns and compute, and that'll give you your F-stat and your p-value, okay? And then using your F distribution calculator, you can calculate critical values for given probabilities in the tail. Okay. All right, everybody good? So far, so good? Should we stop or should we go on?
Go
We
on.
should keep going.
Keep going? Okay. All right. Okay, let me see if there were no questions in chats yet. Okay. All right, let's keep going. Let's go back to the document. Okay. Okay, now this is number 13 in your text. And here we have some departure delay time data for American Airlines flights from New York to Los Angeles. Now, some of us have made that journey before, and it's typically a nonstop flight. Hopefully it's a nonstop flight. Okay, and so let's look at these different flight numbers. Flight 1, Flight 19, Flight 21. Negative values correspond to flights that departed early. That would be nice. It looks like if this data is real data, it looks like there were several flights that did depart early. So their departure delay time would be listed as negative. Okay. All right. And so we're going to use, again, the 5% significance level to claim that, or test the claim that the different flights, typo here, have the same mean departure delay time. Okay. So let's test that claim. All right. Again, the boilerplate listing the null and the alternative here. And in each of these 3 examples that we've done so far here, K has always been 3, hasn't it? But it doesn't mean that K is always 3. This could be 4, 5, and so on, okay? All right, and again, the degrees of freedom depend upon the number of flights here for the numerator, and for the denominator, we'll compute it based on both the number of flights and the number of samples in each of these 3 populations here, okay? Okay, do you want me to go back into StatCrunch to show you how we calculate the F-stat? Yay or nay? Going once? Going twice? Okay, so again, when we go back to StatCrunch, you'll see the data listed there. And if I do my F-stat test using, again, stat, one-way ANOVA, and choosing my columns, we have time. Let's do that one more time, okay? Here are the flight data here, okay? And if we go back to stat, one-way ANOVA, go down and pick out our flights here. Let's, I have the dot plot in the solution set, and now we compute, and here we get our test statistics for the one-way ANOVA for the test of the 3 mean delays and departure times, and we get the following result, okay? All right. Here's our F-stat, and here's our p-value. Our p-value is greater than 0.5, isn't it? Sorry, greater than 0.05, all right? So we would fail to reject in this case, and look at your F-stat, it's also small. Okay, now while we're here, we'll go ahead and calculate our critical value using our F distribution. Okay. And notice that your degrees of freedom for the numerator and the denominator are given here using the formulas that we used in the previous two problems. K minus 1 is 2, and K times n minus 1 is 21. Whoops. Okay. All right. So we have our degrees of freedom as 2 in the numerator, 21 in the denominator. We'll put area 05 in the right tail, change our inequality to greater than or equal to, and we get a critical value on the F curve, under the F curve here, to be about 3.5. All right. And that's summarized here in our okay. All of this data now has been copied and pasted into our document. And here we see our p-value, our f-stat, and then down here we have the critical value, about 3.5. Okay. And do I have the dot plot here? Yeah, here's the dot plot. And what happens here is that you see large dispersions for flight 21 in delayed departure times. Okay. And even though the sample mean for the delay times is not that far off, you know, it'll get pushed out a little bit because of this, because of the dispersion. All right. So that's what gives a high p-value here. Okay, we have a high dispersion in flight 21, and that'll lead us to, okay, turns out that we don't reject, and we conclude that the means are equal, right? Okay, and that's also borne out by the comparison with the critical value. The critical value is 3.5, but our f-stat falls to the left of that. So that would lead us not to reject. High p-value and a low f-stat, okay? Okay, and the last problem, we're doing pretty good on time here. Listed below are attribute ratings by females who participated in speed dating events. Never had the the experience of participating in speed dating, but it sounds like fun. Okay, use a 0.05 significance level to test the claim that females in the different age brackets give attribute ratings with the same mean. Okay, so here are the speed dating results that females gave, and these are attribute ratings. And now the one-way analysis of variance has split the females into 3 age groups. And so is there a difference across the age groups measured by average attribute across the 3 age groups? That's what we're testing here, okay? So again, the boilerplate information gives us the null hypothesis. And remember, we have 3 age groups. StatCrunch, of course, can treat a larger number of categories here, or age groups. Okay, but in this problem, we just have the 3 age groups. We have the sample data for each of the 3 age groups. And let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have a sample size of 10 under each of the age groups. Okay, there's our sample size. Here are the average attribute values across the 3 age groups and their standard deviations, okay? And notice that the p-value is high. So H naught will fly. We have a low f-stat, and therefore there is not sufficient evidence to warrant rejection of the claim that females in the different age brackets give attribute ratings with the same mean. And furthermore, age does not appear to be a factor in the female attribute ratings. Okay, here is our F distribution. And okay, so we took our K value, which is 3, K minus 1 is 2, N here is 10, and 3 times 10 minus 1 is 27. Okay, so those are the correct degrees of freedom. Set your right tail probability to be alpha, which is 0.05. And so that'll give us a critical value of about 3.35. And that's all summarized in your solutions here. Okay. Okay, 0.23 is our f-stat given to us from the one-way ANOVA back in StatCrunch. All right. Okay, guys, that's the 4 problems from your textbook. And now, when do you want me to post this to announcements? You want to work on it? And yep, Friday at midnight. Or post it ASAP. What would you like?
ASAP, please.
All right. Okay, I'll go ahead and post this to announcements today. And your StatCrunch session will be saved off. All right. And then you'll submit that along with your document. Okay. And I am remiss, I have to catch up, grade all your worksheets, and I promise to have those grades to you right after Thanksgiving. Okay. And so you'll have that in your back pocket. You'll know what your worksheet grade is. And you're all working feverishly, I hope, on completing your MyLab statistics homework. There won't be a Zoom session next week. So the next time, let's go back, before we leave here, let's go back to the announcements. Sorry, let me see. Okay. So in your announcements, I've given you several markers there, dates. Okay, so no Zoom session next week. I'll post the solutions that we just went over to your announcements today, so you'll have that in your back pocket. And so you'll submit this worksheet by midnight this coming Friday. So your worksheet 12 will be due Friday midnight, okay? And bullet 7 here, okay, when is your MyLab statistics homework due? That'll be due midnight last day of the semester, which is December the 14th. That's a Monday, okay? How about your final exam? Okay, your final exam. By the way, I will post a practice exam, and we'll go over that in our Zoom session on Thursday, December the 3rd. That's the first Thursday after we come back. Okay, so that'll give you plenty of time. You know, I won't post it until around November the 30th. So you'll have at least 3 or 4 days to look at the practice exam, and we'll go over it on Thursday, okay? There's another option that we could do this Zoom session on Tuesday, December the 1st. Somehow I think our class has preferred the Tuesday Zoom session, and I get pretty good attendance on the Tuesday session. So any thoughts on that before we, that's a long ways off, I know. Maybe you don't want to think about that one yet. Shall we keep it at Thursday unless I get some feedback to do it on Tuesday the 1st? Keep it at Tuesday the 1st rather than Thursday the 3rd. All right. Okay, so we'll leave it at Thursday the 3rd for the time being. Let me check your chat responses here. November the 19th is a Thursday. Sorry. Okay, so yeah, there's a typo here, isn't there? Okay, I have here Friday, November the 19th. Okay, that should be the 20th. Sorry. Okay, so it's due Friday, November the 20th. Okay, good. There was one other thing there. Let me, before we end the meeting, let me just look at this one more time. Okay. Okay, so our next meeting will be the practice exam, going over the solutions to the practice final on Thursday, December the 3rd, unless I get an overwhelming response that you'd rather do it on Tuesday after the Thanksgiving break. Okay, I think the Thursday will give you a little time during the start of the week to open up your practice exam if you haven't already opened it, and that'll give you a few days extra before we go into the practice exam solutions on Thursday, December the 3rd. Okay, guys, I've talked a lot, so I will end the meeting now unless there are any questions. And then I have office hours this morning also, starting at 11:30. Okay, thanks, guys, and have a good Thanksgiving. See ya after Thanksgiving, okay? Bye now.